So I would like to start with this colorful representation of a new sensor fusion technology that is called dynamic grid. We believe that this technology is an enabler for next generation driving functions, and in the next few minutes I would like to show you why. Let's have a look at typical driver assistance systems or automated driving functions as we can see them today in the market. Typically they consist of several blocks that you can see down there. So we have typical sensors like radars and cameras. We have some sensor fusion block that comes afterwards, which provides an environmental model that goes into the actual driving function. And then finally we have the vehicle control, like steering or braking. So if you look at those current generation systems, then they typically operate in well-structured environments. Additionally, if you look at the traffic participants and the objects that those systems need to be able to detect, then very often they have at least similar behavior and similar properties. So they share a lot of these properties. Furthermore, typically we have a limited number of scenarios that those driving functions need to support, and we are all aware of the typical functions like assisted parking, emergency braking or ACC on highway scenarios or highway regions. We have lane keeping and also rather simple warning systems. So typically those driving functions and also the sensor fusion, they use what we call low resolution radar sensors. And if you have a closer look to those sensors, then we will see that they provide very typical values like a 2D position plus a velocity, Doppler velocity of the objects. In general, those sensors provide a very small number of detections per object. You can see this on the right side, so very often you get only 1, 2, or let's say maximum 3 detections per object in the vehicle surrounding. And from a technical point of view, those sensors, they typically provide an object level output that is often meant to be used for standalone applications, so which means that the sensor includes all the things, also the driving function, and then directly connects to the control of the vehicle. On the other side, we have camera sensors that are already used in systems out there. Those camera sensors, they typically provide bounding boxes of the objects. Again, the number of detections per object is really low. Typically, we have just 1 detection per object, and this is also the reason why we call those cameras low-resolution cameras. And once again, also these sensors, these cameras, they are typically meant to be used in a standalone manner, so directly connected to the vehicle control. Let's have a closer look to the sensor fusion that is widely used for those current generation systems. And this is what we call dynamic object fusion or tracking. They have the advantage that they require exactly the things that those sensors provide, so low resolution sensors, that's what they use on the input side. On the other hand, they require that all the objects that you need to be able to detect for your function, that those objects, that they are known at design time, so that you can properly model them in your system that is typically realized using classical Kalman filter approaches. Those systems or the sensor fusion approaches, they have the advantage that they are well suited for large distance tracking of dynamic objects. So that's where they have their main advantage, I would say. That's why they are also used for things like ACC or AEB in highway scenarios. However, on the other side, those algorithms, they have very limited performance for near distances. or for small distances, and what we call extended objects, so objects that have a length and a width. That's where we really see the limits for these algorithms. And additionally, as the name indicates, the name of the approach indicates, they do not have any support for static environment, so this is completely out of their scope. Let's have a look at the next generation sensors that are upcoming or already in use in some vehicles. Like low-resolution radars, they provide a position of the objects and plus some Doppler velocity, but in contrast to low-resolution sensors, high-resolution sensors provide much more detections for all the objects. And as we deal with radars here, you can see that the detections do not only come from the contour of the object, but they may also come from inside. You can see this on the right side on that vehicle, where we have this schematic view of the detections. This is important to know. We have large number of detections per object, and from a technical aspect or from an interface perspective, those sensors, they provide their data at detection level, and they are meant to be used for low-level fusion. Let's have a look at some real data. So here you can see a very typical urban scene where we have some cars in front of us, and in the center we have a bird's eye view with all the detections of some radar systems that are installed in the host vehicle. And I would like to highlight a special, let's say, sweet spot or point here in the middle. You can see this on the lower left side. There we have 3 vehicles, and they are represented by those detections on the right side. So you see, for those vehicles, we get many detections. And I would say that's the new point that we need to be able to handle when it comes to next generation radar sensors. Let's have a closer look to the next generation camera sensors. Here, many things change compared to the previous versions. While we had bounding boxes in the past for cameras, now many people in the community are using cameras that provide what is called semantic annotation, and sometimes you even get direct depth information from the camera. It's completely different to the previous cameras that we had in the market, because now this information is provided on a pixel level, which means for each and every pixel in that image, you get the information, what class this pixel belongs to, be it a vehicle, a pedestrian, a truck, and so on. And sometimes, or some cameras even can provide depth information on a per pixel basis. Last but not least, for next generation driving functions, more and more LiDAR systems pop up in the market. We completely, let's say, kind of ignored that for the current generation, but now LiDAR sensors are coming. And similar to radar sensors, we get a huge amount of data here. It's a bit different than the radar, because now we get the points on the contour. You can see this on the vehicle on the right side. And again, this or those sensors provide its data on a detection level for being used in a low-level sensor fusion approach. Let's dive into the requirements of the driving functions of the next generation driving functions. So in contrast, or in addition to the driving functions that we have in the market right now, these functions typically also operate in urban environments, which change a lot in terms of the sensors, the scenarios, the sensor fusion approaches, and so on. We see many different traffic participants, like pedestrians, we see bicycles, trucks, and so on. And in addition to these well-known types, we also have unknown object types that need to be handled at least in some way in urban scenarios. Of course, the number of scenarios is increasing, and their complexity is much higher than in previous versions. I have some typical function names here things like automated parking, city AEB, automated steering, but also ACC functions are coming to the city. Traffic jam pilot will be there, but also systems like highway pilot will make use or will have those requirements. If we look at the environmental model, that is the input for those next driving functions, then we have additional requirements compared to the previous generation. The first one is that now objects really have what we call extensions. So they have a length and a width. This is very important for the driving functions. For instance, for correctly associating or assigning the lane that those traffic participants are driving on. It also requires to have prediction or motion prediction so that we know where those traffic participants will be in the near future. Well, those two properties, they apply to the dynamic objects. In addition, the new driving functions also require static objects that are indicated in red here. And furthermore, as soon as the driving function wants to do steering and plan some path that it then can drive, then this function also requires free space information. I already mentioned that the systems need to be able, at least to some extent, detect and track unknown object types, so object types or objects that are not being known during design time. And of course, this environmental model needs to support high-resolution sensors on its input side. Let's have a look how those requirements are being tried to meet with current generation sensor fusion approaches. So if you look in the market and in the industry, then you typically see a combination of a dynamic object fusion and a so-called static occupancy grid fusion out there, this combination tries to address the mentioned requirements. Let's start with dynamic object fusion. As I already mentioned, due to the Kalman filter approaches and the so-called point source assumption for the object, this approach has very limited performance when it comes to small distance tracking. And it's also very limited in terms of gathering the extensions, the length, the width, even the height of those objects from high-resolution sensors. It requires that all the object types need to be known in advance during design time. And this introduces some risk to miss those unknown dynamic objects on the road. Furthermore, if you really want to use high-resolution sensors with dynamic object fusion, then this requires what is called a clustering approach, a pre-processing which comes before the actual sensor fusion and tracking. And this pre-processing step tries to cluster, to group multiple detections of the radar, let's say, and then, for instance, provide those red bounding boxes that you can see on the right side. If the clustering would perform as depicted in the image here, everything would be fine and the dynamic object fusion would provide correct results. However, in practice, it's a bit different, and those clustering approaches, they are very error-prone because those approaches, they need to take the decision which detections belong to which object at a very early stage here, and they do not have enough information for reliably cluster those detections. And this, of course, produces errors in the dynamic object fusion. On the other hand, we have static grid fusion approaches. From an interface point of view, those approaches, they provide static objects and free space. It's exactly the thing that those new driving functions require. But there are some drawbacks, and if you look at the right side, with the green and the red representation, that would be the ideal output of such static grid fusion. In practice, again, it's a bit different, as we have dynamic objects in the scenes. That means that real static grid approaches look like that. We have lots of dynamic objects inside, often with heavy tails as soon as those objects are really moving in the scene, and that this would result in false positives for the free space and also for the function. A classical workaround for this is that engineers try to exclude the measurements from the dynamic objects and do not put those measurements into the static grid fusion. While this theoretically works, this approach relies, once again, on the dynamic objects that we just estimated with the dynamic object fusion. And as soon as the dynamic object fusion makes errors, for instance, due to the error-prone clustering, then those errors, they propagate through the system, which means that if the dynamic object fusion makes an error, also the static grid fusion makes an error, which increases the risk that those systems fail in challenging scenarios. Due to those limitations, we decided to invest in a new kind of algorithm that we call dynamic grid fusion or dynamic grid. So what is this dynamic grid? In contrast to the approaches described before, the dynamic grid can estimate the static and the dynamic objects as well as the free space in an integrated fashion, which means this approach resolves that kind of chicken and egg problem that the previous approaches had, where we need to know the dynamic objects for the static objects and maybe vice versa. So this is really an improvement here that we can see with this approach. The approach does not require any clustering, which would introduce those errors, and due to that we have no error propagation to early decisions. The dynamic grid uses much more information to distinguish between dynamic and static objects, and thus provides much more robust results for the driving functions. Of course, it supports high-resolution sensors like HD radars, cameras with semantic segmentation, but also high-resolution LiDAR sensors. Up to some extent, it has built-in support for unknown object types, and this support comes from very few modeling assumptions that this approach takes, which also means that the amount of training data that is required for this approach for learning the parameters is really low compared to, let's say, AI-based method. Let's have a look how the result of the dynamic grid looks like. So here you see in the center the host vehicle in blue, which drives in an urban environment. You can see in green all the free space that the algorithm provides or estimates. You see in red all the static objects that are there, and in blue all the dynamic objects. For the dynamic objects, you additionally see those curved lines. That's the predicted motion from the dynamic objects, which means that the motion can be predicted up to a certain point in time into the future. Now we enter a roundabout, and you may watch at the vehicles, the other objects, how they are tracked in the roundabout, how also the prediction works here in such complex scenario, but also the static objects, how they are estimated and extracted from the algorithm. I would like to highlight some of the properties of the grid fusion approach. First thing is the current sensor fusion approaches. They have some inherent limitations, and those limitations, they make it really hard for those algorithms being used in next generation driving functions and coping with the complex driving scenarios that we have in these functions. Second thing, integrated sensor fusion approaches resolve those limitations and thus serve as an enabler for next generation driving functions. On Baselab's side, we provide this as the Baselab's dynamic grid. We optimize the algorithm for CPUs, which is also very important when it comes to embedded and production. The approach supports high-resolution radar sensors, cameras with semantic segmentations, and also LiDAR sensors. And, very important, it is available now. I would like to thank you for your attention, and now I'm open for potential questions.
Excellent. Thank you very much for your presentation, Eric. It's fantastic to see how Baselabs is enabling next generation driving functions, specifically with the dynamic grid. So let's see, we have one comment, which is not a question, which is also what I've repeated. One of the audience has just said, hello, Eric, thank you for the presentation, which is always, that's also excellent feedback. So I can see that someone's typing. Here we go. Next question has just come in. Thank you for the speech. Can you comment, please, if your approach covers 3D sensors?
Yeah, I guess this addresses, for instance, LiDAR point clouds, where you get also 3D information. Currently, the approach addresses 2D scenarios, which means you can use 3D sensors on the input side, but the output is a 2D representation. So LiDAR point cloud, 3D LiDAR point cloud information can go in. However, the output representation would be 2D.
Okay, super. The next question that we've received here is, how do you consider environment condition for sensor fusion?
I guess this addresses things like weather conditions and things like that. Maybe a general comment on the things that also Baselabs offers here. So what we offer is a technology. It's not a kind of a ready-to-use component. So what we offer to our customers is that technology. If you have different weather conditions and if your sensor is able to cope with these conditions, then of course you can use with those weather conditions. On the other side, this dynamic grid can also be, of course, configured to cope with different conditions, as long as those conditions are known to the systems. I would like to answer it like that.
Okay, so we've got 3 more questions, and I'm sure more will come in as you answer. So the next person has 2 questions within one. Okay, so it says you didn't mention sensor synchronization, which is a big challenge within data fusion. Are there any new solutions to avoid sensor latency within fusion? Often radar is slow compared to cameras. That's the first question.
Yes, that's a very important aspect and topic. In general, the approach dynamic grid is able to deal with asynchronous sensor inputs. However, especially if you have things like out-of-sequence measurements, as you mentioned, if the sensor is slow, then in addition to the actual sensor fusion approach, you need approaches for handle those out-of-sequence situations, like deterministic buffering, which is also part of our offering. But that would be my answer. Using things like deterministic buffering can at least reduce the effects on such asynchronous sensors or out-of-sequence measurements from these sensors.
Super. And from the same person, the second question in relation to this, about dynamic grid fusion, does it mean there is no more object classes strategies, in brackets, pedestrians, cars, trucks, bikes, and then control law strategies shall be redefined?
Yeah, that's also a highly relevant question. Thank you for that. Well, indeed, we believe that despite the fact that we now have the dynamic grid approach for sensor fusion, we still need object representations on the output side. I already tried to show that in the video before, where we had where we also extracted objects from the dynamic grid. So the dynamic objects with the rectangles and the the driving direction, but also the free space extracted in a parametric way. Because we also believe, as you mentioned in your question, that driving functions will continue to operate on object level, and that's why the grid approach is one thing. In addition, there is an object extraction method required for those driving functions for sure.
Okay, and then we have two further questions. Starts with, thank you for the presentation. My question is about the computation and real-time issues with the high amount of data in case of high-resolution sensors, and then in brackets they've written low-level fusion.
Yeah, that's exactly the thing where we really invested lots of time and efforts and manpower to bring that approach on standard CPUs, and in contrast to this, not using any GPU-based machines. This was important for us to lower the computational load, which means that this approach can be run or runs in real time on an A72 from ARM CPU. So this is, I would say, one of the major outcomes of our efforts here. And this makes this approach real-time capable and also capable for production for next generation systems.
Okay, the questions are flooding in. So I'll ask the final one here, but a reminder to everybody within the web app, you can connect with Eric directly after the event.
Sure.
So I'll ask the final question here, and then Eric, what maybe we can do is you can see the questions, I believe, in Zoom. You can also give written answers. I know you've given them verbally, but if you want to put it out there again, then people can see this too. So the final question for your session today, and thank you everyone for the questions, is thank you very much for the clear answer. Does it mean object classes are directly defined directly by dynamic grid fusion, or high definition sensors are still providing object class information as inputs?
Yeah. The classification, so the classification information still comes from the sensor side. So the dynamic grid is able to use that information, and so it can feed that into the dynamic grid, and it can also be used for later a grouping of the objects. But the information still comes from the sensor side. That's for sure.
Okay, super. Well, lots of questions there. You can see them all, Eric, in the system. I've also got screenshots for you if you can't see them from where you are right now. And hopefully we can also get some written answers from you too that we can share with the audience and add to the web app in your virtual profile and exhibition area too. That would be fantastic.
Yeah.
Okay.
I can do that. Thank you.
Okay, super. Well, thank you very much, Eric. I will now end this recording and we will move on to the next presentation. Thank you again.
Thank you.